Great. So I just want to quickly just show you the updates in the concept card so that you just can run through that. So this is the Cauchy's equilibrium for forces in X and Y and moments that we ended off with. I included quite a number of slides on tractions. So this is just to make sure that you get comfortable with what we've discussed on the light board, different notations. I'm asking you how to do this. If you're not sure, go and watch the light board, but essentially the tractions get dotted with a normal and there's S vectors to get the normal and the shear components of the stress tensor out. So that is important to understand that these components are now shear, are the stress components that you get out. Take a note here, please. Although this is an inclined plane, my traction vector is still in the XY coordinate system. It's a component. So by taking this XY component coordinates and dotting it with N, I'm getting a distance along this N vector. Dotting it with S, I'm getting a distance along this S vector. And now I've expressed this vector in terms of this coordinate system. Okay, so just making sure we come through that. Here's a couple of additional examples. So this was that traction vector to, what was this one? Stress traction vector. Why do I include this one here now? That was part of the derivation that we did. Anyway, this is again just to show you for if I choose my normals aligned with my X, Y coordinate system. So what I'm doing now is I'm having sort of N1, S1, N4, S4, N3, S3, N2, S2. So I'm calling these surface 1, 2, 3, 4. Bear in mind, doesn't matter what I call these things, N1, S1, or NX, NY. Just look with your eyes what's going on. Ask yourself what the normal and normal is. Just trying to try and get you comfortable with different notations that you might see, but also just it forces you to think a little bit when you see these things in a little bit of a different notation. Sometimes it's very good because it makes double sure that you understand what you're doing. Then here I'm just looking at pulling this, taking forces, taking the first two tractions. So we will divide by the areas. Now we're looking at what's going on there. It's similar to the light board example we looked at. And here I essentially look at the same situation, rotate it, asking what's going on, and then we can see what are the kinds of contributions we'll get in TNX and TN2. This tilde is for this traction on this plane, tilde is for that one, and TN3 was originally what was applied in this direction. So this is the traction, so that was sort of applied over that. So what you see is if I were to look at the force acting on this, would be the same as the force acting on this plus the force acting on this. You can check for yourself those aspects. And here's again just loading in both directions like we discussed in the light board. What happens? So if I see here I've got a loading here and a loading here. So what we're seeing is now we essentially will get a contribution of T4 on here and a contribution of T3 on here. So this is what I'm trying to highlight here, is that this final traction here will have a contribution from this and a contribution from this, and this is how you do linear superposition with this again stress tensor. Like I'm just mentioning, it's beautiful how the mathematics just work out. If I have it like this face will only see T3, this face will only see T4. They're nicely uncoupled. But if I rotate the surfaces on which I would like to resolve the tractions, it will do the linear superposition for you. So this is that Q transpose Q, sigma Q kind of operations. If I were to have a rotated plane, all of that, in essence, when you think about it carefully, is how you do linear superposition with stress tensors. So that's all. And then just putting a couple of numbers in. Feel free to walk through this and double check, confirm that you agree with the numbers that I've got in there. Again, just the connection between the stress square and the stress matrix. I'm just showing the full one. Again, just reminding you that this stress matrix that you have contains all the information. So what I just want to highlight here is when you think about it carefully, this stress matrix gives you the traction on all the surfaces. So this is what I'm just demonstrating here, the positives and negatives and stuff like that, but it gives you traction on all the surfaces for any orientation of this square. I can put the square at any orientation, say what are the tractions in this face or this surface or that surface, and everything is contained in this stress matrix. Okay. And then some more just reminders of this in an arbitrary reference frame with a theta there, angle with the normal XY coordinate system, and then just a visual reminder that we take the stress tensor. This Q here is to get the tractions, and then this Q here is to take the tractions and make them stress components. Very simple, very nice, but now you understand hopefully the meaning of these Qs, and also how to construct them by just computing the normals that you have. And if you, this is essentially the bottom line of how I would like you to think and go about this. Okay. Then after that, I've got stress resultants I've got in here. So force in X is the X component of the traction on this face, integrated. Y, and just as we discussed on the light board, so the shear force in Y direction. This is now the forces in this global coordinate system, X, Y, and Z, bending moments around the axis of this global coordinate system, and torsion around this global X-axis. This is what you'll compute with these stress resultants. Okay, then it's the stuff that that I've added in, just planar relations for the constitutive relations, plane stress, plane strain, and then I started off with some slides, additional concept cards on the summary of what to do when you get a displacement field, and the question, give you a problem and a displacement field, and I ask you, is this valid? This is what you need to do. And then here's just the strong form that we've discussed in the videos, and then I've got some function approximation slides in here, and a couple of additional things. So I'm just going to go through, not tell you what's going on, but I'm going to show you that we are very close to getting here. This is the weak form. Now you can see you've taken a problem and transformed it slightly, and now it's integration, and there's weighting functions. And this is the beginning of the finite element method. All right, so hopefully you enjoy those concept cards. Please make sure you get comfortable with them. All right, they're there to help you and just to summarize a little bit, but also to make sure that you can reflect on your understanding if you could follow along what's going on. All right, thank you.